Sand, water, sun. The whole universe is made of atoms. Even children are made of atoms. At least that's what you believe. And it's surely what you learned in school.
We're taught in school that all the universe is made out of atoms, but it turns out that's just the start of the story. There's a whole much bigger universe out there to explore, which is made up of completely different material, stuff that we haven't encountered before, and we're trying to find out what that is.
Today, science is struggling with a mystery that calls into question our certainties. There's now something else in the cosmos, a reality we're only just beginning to glimpse.
Most of the universe is made out of stuff that we have not yet figured out. 95% of the universe we still have to explore.
In fact, atoms only account for 5% of matter in the universe. The rest is still totally unknown to us.
We know what it isn't, but we don't know what it is.
Dark matter isn't supernatural, but its mysterious behaviour certainly brings that idea to mind. In fact, some people call it the ghost matter, because it's this invisible, ethereal substance is all around us, but it just doesn't interact with us at all. It's almost as if it has its own parallel existence all around us.
Across the globe, scientists have embarked on a crazy race, chasing dark matter in the sky, underground, and in outer space. But for now, the more advanced equipment and experiments become, the more they reveal the extent of our ignorance.
What is dark matter? I don't know if I knew what dark matter were.
It's the stuff which fills my dream and doesn't make me sleep at night.
We are at the beginning of a real scientific revolution right now. It's a huge revolution. It's on the scale of the Copernican revolution.
Finding a particle of dark matter would just be fantastic. It would solve what is the biggest question at the moment in science. What is the universe made of?
Why are astrophysicists so convinced of the existence of this mysterious invisible matter? Because without dark matter, the universe wouldn't be the way it is. There wouldn't be enough gravity for stars and galaxies to rotate at the speed we observe.
It turns out there's just not enough stars there. They don't have enough gravity to hold the Milky Way together. Now, it's fortunate for us that there's extra dark matter in the Milky Way. That provides an extra force and keeps the whole Milky Way together. It's fortunate for us because if there weren't any dark matter in the Milky Way, there wouldn't be enough force, we couldn't hold the Milky Way together, and all the stars would fly off into the cosmos.
This story began in the 1930s, but the question wasn't truly asked until the 1970s by the American Vera Rubin. A young mother of 3 children, Vera chose to specialize in a field where competition from male colleagues wasn't too fierce. Rather than observing black holes, she turned her interest to the stars of the Andromeda galaxy. Sir Isaac Newton taught us that in our solar system, the farther away a planet is from the Sun, the more slowly it turns. Vera therefore expected the speed of the stars in the Andromeda galaxy to follow this same decreasing curve. But that wasn't what she observed. The speeds of the stars remained constant, whatever their distance from the center of the galaxy.
She was able to see as you go further and further out from the center of the galaxy, you would expect that the stars would move even slower and slower because they'd be feeling less of the gravitational pull to pull them in, but they weren't. It kept going further and further out with the same high velocity.
Why was it that what was true for the solar system was different for a galaxy? Would Newton's theory need modifying when we went up in scale? Or did we need to come up with a new, extremely heavy matter which would create the necessary gravity for these equations to hold true? The shy Vera dared not contradict the great Newton and opted for the second solution: a hidden mass that allows the stars to rotate just as quickly without being scattered throughout the universe.
The idea behind dark matter is this. There are anomalies in the behavior and dynamics of galaxies. And to understand these anomalies, we suppose that there exists an invisible dark matter which affects the movement of the galaxies. But the origin and nature of this matter remain unknown.
Since this discovery, scientists have strived to prove the existence of this dark matter. But how do you detect an invisible substance?
You can see normal matter because it emits or reflects light, a bit like these trees reflecting the light beam from this flashlight. Conversely, dark matter doesn't emit or reflect light. Light goes right through it. So it really is dark, and the only way of seeing it is to observe its effects on its environment. Imagine that I'm made up entirely of dark matter, so you can't see me. But if I take my cup and drink my coffee, like this, you can't see me, but you can see the cup moving, which proves there is something acting on this cup. And this something is identical to the dark matter in the universe, which acts thanks to the effects of gravity on its environment.
To detect dark matter, Yannick Méliès uses the curvature of space-time, as laid out by Einstein in his theory of relativity.
To understand Einstein's space-time and how rays of light are deviated in the universe, you have to think of the universe as a kind of checked tablecloth grid with a massive compact sphere on it. At each point that the sphere is placed, the tablecloth will be deformed. This deformation is the distortion of space-time in Albert Einstein's theory of relativity. If you now propagate rays of light, they will be deviated by the effect of the deformation of space-time produced by the matter.
Einstein called this effect gravitational lensing, the object constituting the lens being sufficiently dense and massive to bend rays of light. But this phenomenon remained a theory and was yet to be observed until Yannick and colleagues happened upon something strange in the sky in Hawaii. In 1985, Yannick, then a young researcher, arrived at one of the best telescopes in the world, 4,200 meters above sea level, on the summit of the volcano Mauna Kea.
We didn't go there to study dark matter. We went there to study the changes in large clusters of galaxies far from Earth. Suddenly, we detected a very strange structure that looked like an elongated smile, much more elongated than a galaxy, and what's more, very distorted. No astronomical object was listed in the catalogues, so we were faced with a huge enigma, and we set out to try to interpret this object.
What was the nature of this elongated spot on the edge of the galaxy cluster Abel 370? Was it an optical effect in the telescope? That's what everyone believed at the time, because it was thought that there wasn't enough matter in galaxy clusters to deviate light. But Yannick, who had just finished his PhD, and his colleagues, were convinced that this smile was the signature of another galaxy hidden behind Abel 370.
The observer and his telescope are here. And if a galaxy is exactly in line with Abel 370 and the observer, then extremely strong deflection of light rays occurs, leading to the formation of a gravitational arc.
Yannick's reasoning went even farther. If gravitational arcs existed, then there must also be hidden matter that gave enough mass and density to galaxies to bend light. By observing the curve of the arcs, he could now see where dark matter was and how it was distributed across the galaxies. By applying this method widely, he realized he had discovered a fantastic tool for detecting dark matter in the universe. Then began a race against the clock to be the first to publish this discovery.
We published our results, and 2 weeks later 2 other articles appeared, one by a British team and one by a US team, who had independently detected, and with different data, exactly the same phenomenon. This was the gravitational lensing revolution in astrophysics. For the first time, we had found a method for seeing dark matter and measuring and evaluating its presence.
Gravitational lensing might sound like a strange idea or a complicated idea, but actually, seeing light deflected is something that we do every day. Even when we just look through a glass of water, we see distorted images of whatever's behind it. And even though the water's transparent, we know that it's there because of the distortion. Well, in astronomy, it's exactly the same situation. When we see distorted images of a galaxy, we know that there's some dark matter in front of it, and that's our evidence that there is something invisible and massive out there. So, you see, we're actually used to the idea of gravitational lensing. We use it every day.
In Durham, astronomer Richard Massey has made the first 3D map of dark matter in the universe.
Exploring a new topic in science is just like exploring a new frontier in the wilderness. You first map out what it is and then explore it. What we're seeing here is a three-dimensional view of the dark universe around us, and that's shown in blue. That's as seen by the Hubble Space Telescope through the use of this gravitational lensing trick. So let's say we have a hypothetical galaxy on the far side of the universe, shown by this little yellow dot. Now, as the light from that galaxy comes or travels across the universe towards us over on the right, it doesn't travel in straight lines. It gets bent around this clumpy dark matter that it passes near. And what we end up seeing is not a true image of the galaxy, but a distorted one. It's as if the light rays from this galaxy have become bent, crimped and distorted, and we see it subtly distorted. And even though we can't see the dark matter directly, it's those distortions in the images of very distant galaxies that tell us that there is something very heavy, even if it's invisible, between us and them.
Astronomers can now trace the outlines of this hidden matter. But what is this ghostly matter made of? Is it formed of atoms? The particles that comprise sand, water, and even children? How can scientists study this matter, which weighs so heavily on the cosmic balance and which is invisible to our instruments? In the jungle of Puerto Rico, dark matter hunters have built a very strange instrument to peer into the sky beyond the visible.
What we're trying to see is things that other astronomers can't see. To see dark matter, we need a weird machine. When I first came down here, I thought, this is like a giant spaceship traveling between the stars.
Radio telescopes allow us to see what our eyes are incapable of detecting. Radio waves, like infrared waves, X-rays, and gamma rays, are invisible to the naked eye, but we know how to capture them with all kinds of instruments, and they tell us about the objects that emit them. With its 305-meter diameter antenna, Arecibo is the biggest radio telescope in the world. On the ground, 40,000 perforated aluminum panels collect radio waves and send them to this suspended dome, which acts as a receiver. It allows us to observe, in particular, gigantic clouds of hydrogen gas around galaxies. Elsewhere, other astronomers have been gradually discovering dead stars, stardust, and other gas clouds. Are these massive yet invisible heavenly objects the long sought-after dark matter?
We've added together the hydrogen gas we know about, the other gas we know about, the stars we can see, the dark objects we can see through passing in front of other stars, and all of that, we still need about 10 times more mass. And so we ruled out that it could be gas, we ruled out it could be compact objects, and in doing so we ruled out that it could be ordinary matter. And so the only option left was that it was some exotic dark matter. It's as if we're now going into a fourth Copernican revolution. The first Copernican revolution was when we uncentered the Earth. People thought the Earth was the center, and then we said, no, the sun is at the center. The second Copernican revolution was when we said, the sun isn't at the center either. And the third Copernican revolution would be when we said, even the galaxy isn't at the center. The universe actually has no center. But now, we've got to the point where not only are we not at the center, but the very stuff we're made of is only 10% of the stuff of the universe, and 90% of it is this dark matter. And so we really want to know what that is.
Our physics theories only describe a tiny part of the universe. We are indeed made up of atoms, but we are bathed in a totally unknown matter. This cosmological revolution has given a new dimension to the quest for dark matter. We no longer know the nature of the major part of the universe.
We've gone from it's hidden matter phase to it's another type of matter phase. So it has become a much more acute problem than before. Discoveries are being made which show we know less than we thought. A discovery doesn't necessarily increase our knowledge. It increases our awareness of our own ignorance.
what dark matter isn't. We don't yet know what it is, but we may discover the role it could have played in the formation of the cosmos. At the University of Princeton in the United States, David Spergel is trying to uncover the secrets of the very first instance of the universe.
My job is to figure out how the universe works. You need a little bit of persistence, some curiosity, some understanding of mathematics, and an idea how to cook. We have to figure out the cosmic recipe. What ingredients does it take to make a tasty universe?
Since his election as Astronomer of the Year by Time magazine, David Spergel has been trying to describe in simple terms the complex recipes of the universe. In cosmic cuisine, everything depends on the ingredients, the lumpiness, and cooking time.
What I'm going to do is make a cosmic soup. For the dark matter, since we don't know what it is, and we'll make a more flavorful soup, we're going to try several different ingredients. The dark matter could be something like beans, black beans, green beans. It could be something like zucchini, carrots, or perhaps peppers. This green tea here is going to be our atoms. And the atoms that make up the stars are in some ways just a thin frosting on top of the dark matter. This hot water here is going to be our radiation. We'll add that on top so we can steep the soup. This is starting to look like the universe back in its first few 100,000 years, when it was an opaque place where we couldn't see through it.
Astronomers believe this particle and radiation soup remained opaque for 380,000 years after the Big Bang. The universe was an extremely hot magma, and so condensed that it formed a milky fog in which light particles were unable to propagate. But after 380,000 years, the universe expanded and cooled sufficiently for light particles to be able to move around. And a gigantic flash of light spread through space. The light particles emitted at that instant then began a long journey. $13.7 billion years later, in 1964, two scientists in New Jersey, Arno Penzias and Robert Wilson, intercepted this light by chance. They picked up some background noise that they couldn't explain. The signal was so weak that they first thought it was a defect in their radio telescope due to pigeon droppings. They cleaned the antenna and did the necessary tests. These were indeed waves from this primordial light. Deformed and cooled after their long journey through space, they had finally reached Earth in the form of a very weak radio signal. Penzias and Wilson had just discovered the pale echo of the formation of the universe. But astronomers needed to obtain a more precise picture of this event. On June 30th, 2001, the WMAP probe was launched into orbit 1.5 million kilometers from the Earth in order to analyze this relic radiation. Its aim? To capture the instant when light came into being and to map out the nascent universe.
What's wonderful about studying the microwave background is you're looking back in time, back 13.7 billion years, to a time when the universe was very simple. So I like to think about what we're doing is taking the universe's baby picture. And my job is to look at the baby picture and try to figure out from the baby picture where the baby come from and what will it grow up into, and put together a story of how the universe formed and evolved.
Here is the first picture of this baby universe, a mere 380,000 years after the Big Bang. The red zones are the hottest and densest parts. The blue zones are the coolest. These minuscule differences in temperature are vital clues in understanding the future structure of the universe.
The pattern we see in the sky, in the microwave sky, are tiny variations in temperature due to variations in density of the universe. So this point here might be a few hundred thousandths of a degree colder than this hot spot over here. These tiny variations were basically produced by the dark matter. The dark matter was lumpy, and its gravity attracted the radiation and the atoms. And we wouldn't see the pattern at all on small scales if it wasn't for the dark matter.
In 2011, after 7 years of analysis and thought, David Spergel came to an astonishing conclusion.
Without dark matter, the 13.7 billion years since the Big Bang is not enough time to form the structure we see. Dark matter is an essential ingredient for providing the seeds around which gravity makes galaxies grow. And without these seeds, we wouldn't see the universe we see today.
Dark matter supposedly acted as a catalyst in the formation of the structures of the universe, providing the skeleton around which atoms of ordinary matter gathered to form galaxies. But is there a way of testing this scenario? How do we know whether our understanding of the universe is on the right track? For this, scientists work like detectives, reconstructing a crime scene. And, as the stakes are high, cosmology labs are racing each other to trace the history of the universe after the Big Bang. As it is impossible to see dark matter at work, scientists try to simulate the process on their cosmology machines.
This is the cosmology machine. 3,000 individual computers working together. It can perform 30 million arithmetic operations every second. This is awesome computing power, but that's what it takes if you want to simulate our universe.
There are about 8.6 billion particles that we used to make this simulation. We ran it on 14,000 of the latest processors on NASA's biggest supercomputer. We called this simulation Bolshoi, which is the Russian word that means big in the sense of great or grand.
Everything we see in these simulations is in fact invisible. Only dark matter is represented, seen forming structures in filaments, which went on to form galaxies.
If you try to make a universe without dark matter, it's a disaster. The dark matter is the architect of a universe. Without dark matter, there would be no people, and there would be no human mind capable of asking the question, Why is the universe the way it is? What makes it work?
These simulated universes tell a fantastic tale. One that a number of human minds have concocted from their fascination with light emitted by the universe 13.7 billion years ago. According to this tale, dark matter is the cradle of the stars, and the stars forged the atoms of which we are made.
Dark matter is our friend. Dark matter allows us to exist. It's in the stars that the heavy elements form: carbon, oxygen, nitrogen, iron, the kind of heavy elements that we are made of. We and rocky planets like Earth could not exist if it were not for generations of stars building up the heavy elements within the centers of these big dark matter halos that host galaxies. So we would not exist if the dark matter had not formed.
To find out if their hypotheses are correct, cosmologists compare their simulations with reality. Although they use slightly different parameters, each is convinced he has the right recipe.
You feel like you're playing God, making a universe in a computer. Here is a galaxy made by a computer compared to a real galaxy. I can hardly tell them apart. We've got the right recipe: exotic dark matter and visible matter. And I can tell you that there are few more exciting moments than to see the computer produce a galaxy just like those that our telescopes see in the real universe.
The simulations reveal that a hidden matter has been sculpting our universe for billions of years. But is there a way of proving what truly happened? If science could capture a single particle of this dark matter, the greatest mystery of modern physics would be solved, followed by a Nobel Prize. This crazy race is the new holy grail of particle physics.
It's a huge challenge because it's a question of what the universe is made of. Physics can't go on for decades only describing a tiny part of the universe's components. The aim of physics is to identify what are real objects in the universe. And today we must humbly admit that we're incapable of identifying them. So it's a massive challenge.
We've been searching for dark matter for 22 years in the underground lab in Modane. It's been so long, we must be close to finding it.
I always want to be number one. Why would you leave this great discovery to somebody else?
Leading the race are Elena April and Gilles Jabier, both dreaming of the Nobel Prize. But for what obscure reason did the two competitors decide to carry out their experiments in tunnels on either side of the French-Italian border? Why, instead of looking into space, have they buried themselves deep beneath the Earth's surface? The reason the Modane underground lab is buried under some 1,700 meters of rock is that it's imperative that no undesirable particles interfere with the experiment.
Detecting and capturing particles of dark matter is very complex because they're tiny. They have a very low fission section and they rarely leave signals. So the difficult thing is, when you're looking for a rare signal, nothing must be allowed in to simulate the signal.
As strange as it might seem, dark matter particles pass easily through ordinary matter. They are capable of crossing the 1,700 meters of rock and the thick plating of lead and copper that protects this germanium detector. This is where Gilles hopes to record an incredibly rare event, the collision between a particle of dark matter and a germanium crystal atom.
When a particle arrives, it makes the whole crystal vibrate and causes a tiny rise in temperature, about a millionth of a degree, which we measure with ultra-sensitive sensors.
700 kilometers away, deep within Mount Gran Sasso in Italy, Elena April is Gilles' fiercest rival. To detect dark matter, she has opted for liquefied xenon, a rare gas she fell in love with early in her research career.
We have the best detector right now to see dark matter, honestly. It's so because it is, first of all, you can make these very large volumes that you need. You need a lot of atoms, nuclei, because the event is rare. So the larger the better, we always say that. But you cannot just scale it in mass, in volume. You also have to reduce at the same time the background. That's what doesn't make me sleep at night.
As the probability of capturing a collision with a particle of dark matter is extremely low, the detectors, once in place, run blind for a year. This year, Gilles Gerbier got lucky. His detector captured 4 particles, seen here in red, which could be dark matter. But statistically, 3 of them could be background noise.
This data is inconclusive, so all we can do is make even more sensitive, more high-performance detectors and start over. Set up the new detectors, wait for a year, then recalculate the background noise and open up the box again.
Across the globe, hundreds of other researchers are dedicating their brainpower and sleepless nights to improving their detectors. But despite all their efforts, the particle remains elusive.
You have to be crazy to do what we are doing. Honestly, you cannot go on for so many years after something which doesn't show up. I don't know if it's frustrating or almost killing you. The thought of putting so much energy and effort in an experiment which eventually will not find anything, it is very, frustrating.
Some problems take a long, long time to solve. The existence of the atom, for example, was suggested by Greek philosophers 2,500 years ago. But for thousands of years, the existence of atoms was hotly debated. The question wasn't answered until the early 20th century. So sometimes it takes over 2,000 years to ascertain that an imagined object exists for real in nature.
For researchers in the dark matter race, failing to identify it for such a long time is unbearable. As it's so hard to capture, let's make it ourselves, some scientists have suggested. Let's reconstruct the Big Bang, have replied the more daring among them. In the end, it's in Geneva that 10,000 researchers are taking part in the world's biggest ever scientific experiment. Like everything concerning dark matter, the essential thing is invisible. Hidden in a tunnel some 27 kilometers around and 100 meters underground, the LHC is the largest particle accelerator man has ever built at the astronomical cost of 9 billion euros. Daniel Denegri is a founding father of CMS, one of the LHC's two giant detectors.
With the LHC, both in the CMS experiment and the ATLAS experiment, we approach the problem of dark matter differently to direct detection. In direct detection, you look for pre-existing dark matter, the residue of something that happened 13.7 billion years ago. With the LHC, we produce it. Through collisions that take place in this machine, collisions with a very high energy level, we reproduce locally the thermal and material conditions of a phase in the Big Bang, when particles were produced for the very first time in the history of the universe.
How do you create, 100 meters underground, Big Bangs that give birth to new particles of dark matter? Two beams of particles are accelerated at high velocity before colliding in a minuscule space, measuring 1,000th of a billionth of a centimeter, and for an infinitesimal instant, 1,000,000,000th of a second. Will all these billions of particles, collisions analyzed, and euros invested succeed in making the invisible visible?
The probability of a particle of dark matter being produced in a collision is extremely low. It takes 1,000,000 billion collisions to produce one such particle. And then you have to isolate this particle from all the background noise.
The stakes of this research are so high that results must be confirmed by two independent sources. For this, two competing experiments, CMS and ATLAS, used the same particle accelerator within the LHC. Which will solve the great mystery of the matter of the universe? Each of the two teams is praying to the heavens in a very strange way.
This is the cave where the ATLAS experiment is taking place. Behind me are the millions of detectors we've installed here. The detector is the size of a cathedral. It's as if we've built a whole cathedral 100 meters underground.
For now, the miracle is yet to happen. But here's what Bruno Mansoulier expects to see one day.
If there were a particle of dark matter, it would cause a very particular collision, because we'd see lots of particles produced on one side, let's say on the left, and nothing on the other. And this nothing would mean that the collision has produced invisible particles. And these invisible particles could be dark matter.
Once again, we'd only see dark matter if we saw nothing, or merely the trace of its passing.
Finding this particle would be huge intellectual and scientific progress, the kind man makes once every 100 years, like the discovery of relativity and quantum mechanics. These are massive steps in our understanding of human knowledge.
It would be an amazing discovery because a result coming from particle physics could solve a problem that only exists in astrophysics and cosmology. So there would be a marriage between the infinitely small world, the world of particles, and the infinitely big world, that of cosmology.
A final experiment may solve the mystery of dark matter. Since it is so difficult to capture this particle, or even to make it, researchers will attempt to find its trace in an indirect way in outer space. Direction: the International Space Station, well beyond the Earth's atmosphere. Leading this scientific first is American Nobel Prize winner Samuel Ting.
The International Space Station is the size of 3 football fields. The cost is about $100 billion, therefore it's about the cost of 10 LHC. On this facility, there is one particle physics experiment, and that is AMS. The purpose of this experiment is to see what is the origin of dark matter.
With this new experiment, scientists are stretching the boundaries of the possible even farther. If the theoreticians are correct, when 2 particles of dark matter collide, they should produce a very special cosmic ray that the AMS detector should pick up. The experiment began in May 2011, when Mark Kelly and his team installed the detector on the International Space Station.
We just installed the alpha magnetic spectrometer. It's a $2 billion cosmic particle detector, really a premier physics experiment that's supported by 16 different countries, 600 physicists. We got it successfully installed on the space station. It's a great day for science.
Your support and fantastic work has taken us one step closer to realizing the science potential of AMS.
Well, thank you, Sam. I was just looking out the window of the orbiter, and AMS looks absolutely fantastic.
Samuel Ting has already received the Nobel Prize for his discovery of a subatomic particle. Will he find in outer space the mysterious particle of dark matter?
This is really the first time people put a certain type of precise detector into space. So in a sense, you open a new door. What you really can see is very difficult to predict. If you know what you're looking for, and if you found it, you have not learned anything. The important thing is to find what you're not expecting. That's how science advances.
While scientists hope each day to solve the mystery of dark matter, they are confronted with another enigma. Dark energy, a force that is now thought to make up 3/4 of the energy in the universe, is putting everyone out of joint. This massive unknown has plunged cosmologists into a cloud of fog.
Maybe that all we know about cosmology may be about as much as we're seeing through this bad cloud of fog. We just made things even worse. You know, we already had a mystery of dark matter, and now it's 3-4 times worse because we don't even know what the rest of the energy is, the dark energy.
It was while pondering the final destiny of the universe that Saul Perlmutter made this strange discovery. By precisely measuring the speed of the universe's expansion, he thought he would determine when it would stop growing. But he didn't discover what he expected at all.
The universe wasn't slowing down enough to come to a halt. In fact, it wasn't slowing down at all, it was speeding up. And that was completely unexpected. We did not think that we were going to find a result like this, and it began the whole next odyssey of trying to understand what's going on. How is it that we live in a universe that's accelerating in its expansion?
While the expansion of the universe should be slowing down, Saul Perlmutter's observations show that it is in fact speeding up. A colossal energy must then be forcing the universe to scatter. This discovery, confirmed by another team, earned him the Nobel Prize in 2011. But we still know nothing about this dark energy that governs the outcome of the universe.
Dark energy is something even more bizarre than dark matter because we think it may be a property of empty space itself that makes space want to reproduce itself faster and faster.
This energy of repulsion, totally unexpected and unexplained, goes against the force of gravity, breaking up the universe into billions of pieces.
There's a giant cosmic battle going on at the moment. The universe started expanding out of the Big Bang, but the dark matter, because it has gravity, it holds it together and tries to keep the universe small. But the dark energy seems to be doing the opposite. It seems to be ripping it apart again. So there's this giant battle going on with the dark matter pulling it in and the dark energy pulling it out. And at the moment, we actually don't know who's going to win.
We know almost nothing about the dark forces that govern the fate of the universe. But strangely, we do have a relatively precise idea of our ignorance. Atoms comprise almost 5% of the universe. Dark matter about 23%. And surprisingly, dark energy about 72%. In all, we have absolutely no idea what makes up 95% of the universe.
We have to add two things, dark matter and dark energy. The paradox is that we can explain all the phenomena observed in the universe by adding two components we know nothing about. For a rigorous physicist, maybe we've added too much. Simply to avoid admitting to everyone that we really don't understand very much.
Have the good old laws of physics, Newton's theory of gravity and Einstein's theory of relativity, become incapable of explaining the universe? Dark matter and dark energy are shaking up science and forcing us to drastically review our vision of the cosmos.
If we keep suggesting unidentifiable if entities, can we still trust in the theory of relativity? If there is no experimental proof of their existence in reality, we must doubt not reality itself, but the theory that claims to describe it, and thus come up with a new theory of gravity. There's always a dialectic battle between our theories and the reality that makes physics progress. And the question is, which will yield first, theory or reality?
Is dark matter here to stay? With the discovery of dark energy, darkness seems to have gained ground, at least until we've understood its colossal forces. But until then, we must be satisfied with merely skimming the surface of the world.